Find somewhere comfortable. If you are already lying down, let your body sink a little further into whatever is holding you. You do not need to follow this closely. You do not need to remember any of it. The words will come and go like the sound of rain on a window, and you can let them pass without holding on. We are going to spend some time together tonight thinking about something very quiet and very vast, the invisible ground that holds all of matter together, and there is no hurry at all. The night is long. You have nowhere to be. If today was hard, that is all right. If you are carrying something into this darkness with you, some worry, some sadness, some loose thread of the day that will not stop pulling, you do not need to put it down right now. Just let it rest beside you. It will still be there if you need it. For now, just the soft weight of your body, and the sound of a voice, and the slow, patient universe doing what it has always done. We are going to talk about empty space, about what it is actually made of. And the answer, it turns out, is stranger and more beautiful than you might expect. Picture the space between galaxies. Not the galaxies themselves, not the stars burning inside them, not the planets circling those stars, not the thin wisps of gas drifting between solar systems, but the true gaps between one island of light and the next. Change. The distances out there are so large that the word vast barely touches them. The nearest large galaxy to our own, the Andromeda Galaxy, sits roughly 2.5 million light-years away. A light-year is the distance light travels in a full year, moving at nearly 300,000 kilometers every second, 2.5 million of those years. And between here and there, for almost all of that distance, there is essentially nothing. No stars, no gas worth mentioning, no dust. The temperature is just barely above absolute zero, the coldest anything can possibly be. It is, by almost any measure, the closest thing to true emptiness that the universe offers. And yet, something is there. Something fills that space as completely and as evenly as it fills the interior of a star, as completely as it fills the room you are lying in right now, as completely as it fills the interior of your own body, right down to the space between the nucleus of an atom and the electrons orbiting it, which is, proportionally, almost as empty as intergalactic space. This something has no color, no temperature, no smell. It exerts no push or pull you could ever feel. But without it, you would not exist. Nothing solid would exist. Matter as we know it. With weight, with heft, with the ability to hold a shape and resist being moved, would be impossible. This something is the Higgs field. Tonight we are going to understand what it is, where it came from, why it has to be there, and what it actually does to every particle of matter in the universe. We are going to go slowly. There is no test at the end of this. Just the quiet pleasure of understanding something real and deep about the place you live. To understand the Higgs field, it helps to first understand what physicists mean when they talk about a field at all, because the word is used in a precise way that is slightly different from how it sounds. Think about temperature. Right now, wherever you are, the air around you has a temperature. The pillow beneath your head has a temperature. The wall across the room has a temperature. The street outside has a temperature. Temperature is not a thing that sits in one place. It is a quantity that has a value at every point in space. You can, if you like, imagine drawing an invisible map of the room you are in, and at every single point on that map, writing down the temperature at that location. Some points will be warmer, near a radiator perhaps, or near your own body. Some will be cooler, near a window, near the floor, but every point has a value. There is no location in the room where temperature simply does not exist, where the question, what is the temperature here, has no answer. Temperature is everywhere. That is what physicists mean by a field. A field is a quantity, a number, or a set of numbers that has a value at every point in space. The gravitational field of the Earth is a field at every point in space around our planet. There is a value for the strength and direction of gravity. The electromagnetic field is a field. At every point in space, there is a value for the electric and magnetic influence present there. These fields are real. They carry energy. They are not abstractions. They are the medium through which forces act. The Higgs field is a field in exactly this sense. It has a value at every point in space, but it is different from the others in one crucial and rather beautiful way. Most fields, when left completely undisturbed, when you remove every particle, every source of energy, every influence, relax to zero. The electromagnetic field in a perfect vacuum, with no charges and no currents anywhere, settles to nothing. The gravitational field, far from any mass, approaches zero. The natural resting state at most fields is emptiness. The Higgs field does not do this. The Higgs field, even in the most perfect vacuum imaginable, even in that cold silence between galaxies, even inside a sealed steel chamber from which every last atom has been pumped away, a chamber chilled to within a whisker of absolute zero, a chamber as empty as human technology can possibly make it. A specific, non-zero value. It does not relax to nothing. It cannot. Its own internal physics will not allow it. This is a genuinely strange thing, and it is worth sitting with for a moment. Imagine a room where, no matter what you do, no matter how many heaters you remove, no matter how thick you make the insulation, the temperature never drops below a certain level. Not because there is a hidden heater somewhere, not because of any source you could find and remove. Just because the physics of that room will not permit the temperature to fall to zero. That room would be extraordinary. It would mean the room itself has some intrinsic energy, some built-in warmth that belongs to the space rather than to anything inside it. That is, in a very rough sense, what the Higgs field is. The space itself, the vacuum itself, carries a permanent, non-zero value of this field. Physicists sometimes call this the field's vacuum expectation value, meaning the value the field settles to when everything else is removed. For the Higgs field, that value is not zero. It is a specific number, and that number threads through every corner of the observable universe with perfect uniformity. Now, why does that matter? Why should a field having a non-zero value in empty space have any consequences at all? Because particles are not little billiard balls sitting in a passive void. Particles are themselves excitations, ripples, in their own fields. The electron is a ripple in the electron field. The quark is a ripple in the quark field. And those fields do not exist in isolation. They exist in the same space as the Higgs field. They are, in a sense, immersed in it, the way a vibrating string is immersed in the air around it. And when a field is immersed in a non-zero background, when it sits inside something rather than nothing, the way it vibrates changes, its natural frequency shifts. And in the language of quantum physics, the natural frequency of a particle's field is directly related to the particle's mass. This is the heart of everything. A field sitting in nothing vibrates at a certain frequency. The same field sitting in a non-zero background, in the Higgs field, vibrates at a higher frequency. And higher frequency means greater mass. The Higgs field does not push particles around. It does not slow them down. It changes the character of their vibration quietly and permanently, everywhere in the universe. Picture that sealed steel chamber again, cold, airless, perfectly still. Inside it, no atoms, no light, no sound, and yet the Higgs field is there, at its full value, as present and as potent as it is inside the core of the sun. If you were to somehow create an electron inside that chamber, the electron would immediately feel the Higgs field, would vibrate at the frequency the field requires, and would have the mass we have always measured it to have. The chamber's emptiness is not empty. The ground beneath all matter is not nothing. It is something ancient, something that settled into its present state in the very first moments of time and has not shifted since, something patient and still and everywhere. The question is, why? Why does the Higgs field have this permanent non-zero value? Why does it not simply relax to zero like everything else? To answer that, we need to go back to the 1960s, to a crisis in physics, and to a group of scientists trying to understand why the universe has the forces it does. By the early 1960s, physicists had assembled a remarkable picture of the forces of nature. They understood electromagnetism, the force that governs light, radio waves, the behavior of charged particles, the chemical bonds that hold molecules together, with extraordinary precision. And they were beginning to understand the nuclear forces, the strong force that holds atomic nuclei together, and the weak force, which governs a different and slower kind of nuclear interaction. It is worth pausing on the weak force because it is easy to overlook. It does not hold things together the way gravity does, or the way the strong force binds protons and neutrons into nuclei. What the weak force does is transform particles. Specifically, it allows one type of quark to change into another type, which in turn allows a neutron, which contains a particular combination of quarks, to convert into a proton. This conversion releases an electron and a very light particle called a neutrino in a process called beta decay. And this matters enormously for the Sun. The Sun burns through nuclear fusion, the process of fusing light nuclei together to make heavier ones, releasing energy in the process. But the very first step of the fusion chain that powers our star requires something remarkable. Two protons must come together, and one of them must convert into a neutron. That conversion is carried out by the weak force. Without the weak force, the first step of solar fusion cannot happen. Without the weak force, the Sun does not burn, the stars go dark. The universe remains cold and structureless. So the weak force is not a minor detail. It is one of the load-bearing pillars of the cosmos as we know it. Now, in the early 1960s, physicists were trying to build a unified mathematical framework that would describe both the weak force and electromagnetism together, a single, elegant theory from which both forces would emerge as different aspects of the same underlying structure. This was a beautiful idea, and the mathematics of it was compelling, but there was a problem, a serious one. The framework required that the particles carrying the weak force, the particles that, so to speak, fly between other particles and enact the weak interaction, the way photons fly between charged particles and enact electromagnetism, should be massless. The theory, in its pure and symmetric form, produced force-carrying particles with no mass at all. But massless force-carrying particles behave like photons. They travel at the speed of light. They have an infinite range. A massless particle can carry a force across any distance. Electromagnetism behaves this way. Light travels forever, and electric and magnetic forces technically extend across the entire universe, growing weaker with distance but never truly vanishing. The weak force does not behave this way, not even close. The weak force has an extraordinarily short range. It operates only within distances smaller than an atomic nucleus, roughly 1/100th of the diameter of a proton. A force with such a tiny range must be carried by particles with significant mass. Heavy force carriers move slowly and cannot travel far before their energy is spent, which is what gives the force its limited reach. Measurements and experiments made it completely clear that the carriers of the weak force were not massless. They had to be heavy. Very heavy, as it turned out. The particles carrying the weak force, called the W boson and the Z boson, would eventually be measured to weigh roughly 80 to 90 times more than a proton. So the theory said, massless. The universe said, very much not massless. This was not a minor discrepancy that could be papered over. It was a fundamental contradiction at the heart of the most promising unified theory of forces that physicists had ever constructed. Something was missing. The resolution came in 1964, and it came from 6 physicists working in 3 separate groups, all converging on the same idea from slightly different angles. Robert Brout and François Englert published their paper first in August of that year. Peter Higgs published 2 papers, the second of which appeared shortly after. And Gerald Guralnick, Carl Hagen, and Tom Kibble published their own work in November. All 3 groups, independently, had found the same mechanism, a way to give the force-carrying particles their mass without breaking the underlying mathematical consistency of the theory. Peter Higgs's path to that second paper has a particular quality to it that is worth dwelling on. His first paper had been submitted to a journal called Physics Letters, run out of CERN, the European Particle Physics Laboratory. It was rejected. The editor felt it did not warrant rapid publication, that it lacked sufficient physical relevance. Higgs was, by his own account, annoyed. He revised the paper, and in revising it, he added something that had not been in the original, a paragraph pointing out that his mechanism implied the existence of a new, massive particle, a rickle in the very field he was proposing. This prediction of what would eventually be called the Higgs boson was, in a sense, an afterthought born of frustration. The second paper was accepted by a different journal, Physical Review Letters, and published in October 1964. It is also worth noting that the seeds of the solution had been planted slightly earlier and in a surprising place. Philip Anderson, an American physicist working not on particle physics but on the behavior of superconductors, materials that conduct electricity with zero resistance at very low temperatures, had noticed in 1962 that a similar mathematical problem arose in his field and that symmetry breaking resolved it. In superconductors, the electromagnetic field inside the material effectively acquires a mass, which is why magnetic fields cannot penetrate a superconductor beyond a very shallow depth. His insight came from condensed matter physics, from the study of materials, not of fundamental particles, and it pointed the way for the particle physicists who followed. The solution, in all its forms, rested on a single idea, spontaneous symmetry breaking. The theory could be symmetric, and the force-carrying particles could start out massless, and yet the universe we live in could end up with massive force carriers. If the field responsible for the symmetry broke that symmetry spontaneously by settling into a non-zero value everywhere in space. To understand what that means, we need to understand symmetry breaking itself. The word symmetry, in everyday speech, usually means something like balance or regularity. A face that looks the same on both sides, a snowflake that looks the same when you rotate it by 60 degrees. In physics, it means something more specific, but the spirit is similar. A system has a symmetry if you can change something about it, rotate it, reflect it, shift it in some direction, and the rules governing it remain exactly the same. Here is a simple image to hold. Take a pencil and balance it perfectly on its tip on a flat surface. The physics governing that pencil is completely symmetric in every horizontal direction. There is no reason, built into the laws of physics, why the pencil should prefer to fall north rather than south, east rather than west. Every direction is equally valid. The situation is perfectly symmetric. But the pencil cannot stay balanced forever. The slightest perturbation, a breath of air, a tiny vibration in the table, even the quantum uncertainty in the positions of its atoms will eventually cause it to fall. And when it falls in one direction, one specific direction, out of the infinite circle of equally valid possibilities. The pencil now points somewhere, and that somewhere is special. Even though nothing in the fundamental physics made it more special than any other direction. The pencil has chosen, not consciously, not deliberately, but inevitably. And in choosing, it has broken the symmetry of the situation. The final state, pencil lying in one direction, is less symmetric than the initial state, even though the laws of physics themselves have not changed at all. This is spontaneous symmetry breaking. The underlying rules remain symmetric, but the actual state the system settles into is not. Now apply this to the Higgs field and to the very early universe. The Higgs field has what physicists describe as a potential energy landscape, a kind of map of how much energy the field stores at each possible value it could take. For most fields, this landscape has a single lowest point at zero. The field wants to sit at zero because that is where it has the least energy, and physical systems naturally seek their lowest energy state. The Higgs field's potential energy landscape is different. Physicists visualize it as the shape of a Mexican hat, or sometimes as the bottom of a wine bottle, and both images capture the same essential geometry. There is a raised dome in the center. Surrounding that dome, running all the way around it in a complete circle, is a deep trough, a valley, lower in energy than the central peak. The lowest energy states of the field are not at the center, not at zero, but somewhere in that circular trough. In the very early universe, in the first tiny fraction of a second after the Big Bang, the universe was extraordinarily hot. So hot that the Higgs field had enough thermal energy to sit up on that central dome, jostling around at the unstable peak. At those temperatures, the field was, in a sense, averaged out. Its value fluctuated so rapidly that effectively it had no settled value at all. The symmetry was intact. The force-carrying particles were massless. The theory was, at that moment, working exactly as its symmetric equations described. But the universe expanded. It cooled. And as it cooled, the thermal energy that had been keeping the Higgs field perched at the top of the dome began to drain away. The field became unstable at the peak, the way the pencil becomes unstable when the vibrations stop. It rolled down. But rolled down where? The trough surrounds the dome in a complete circle. Every point in the trough is equally deep. Every direction is equally valid. The field had to choose a specific point to settle at, and, just like the pencil, it chose one, not because that point was special, but because choosing was inevitable. The field rolled to some particular value in the trough, and there it settled. And there it has remained ever since. That settling happened in the first tiny fraction of a second of cosmic history. Physicists estimate the electroweak phase transition, as this settling is called, occurred when the universe was roughly 100 billionths of a second old, at a temperature of around 100 billion degrees. The Higgs field rolled to its resting value at that moment, and the universe has been living with the consequences ever since. Now, why does settling in the trough rather than at the peak matter so much? Because of what happens to the other fields, the fields of the force-carrying particles, when the Higgs field is non-zero. When the Higgs field sits at zero, at the peak of the dome, the force-carrying particles at the weak force are genuinely massless. The mathematics works out cleanly. The non-zero background value of the Higgs field effectively mixes with those fields, intertwining with them in a way that changes their behavior. The mathematical consequence of this mixing is that the force-carrying particles acquire a mass. They can no longer travel freely at the speed of light. They are, in a precise technical sense, heavy. The photon, the carrier of electromagnetism, does not mix with the Higgs field in this way. Its field is structured differently, and the symmetry breaking does not affect it. The photon remains massless. It still travels at the speed of light. Electromagnetism retains its infinite range. But the W and Z bosons, the carriers of the weak force, acquire enormous masses. The W boson ends up roughly 80 times heavier than a proton. The Z boson roughly 91 times heavier. These masses are so large that the W and Z bosons can only travel extraordinarily short distances before their energy is exhausted, which is exactly why the weak force has the tiny range it does. The symmetry of the underlying theory is preserved. The equations themselves remain symmetric, which keeps the theory mathematically consistent and predictable. But the actual state of the universe, the specific value the Higgs field settled into, is not symmetric. And the universe we live in, with massive force carriers and a weak force that operates only at nuclear scales, is the consequence of that ancient, irreversible choice. So the Higgs field settled into its non-zero resting value, and the force-carrying particles of the weak force became heavy. But the story does not stop there. The Higgs field gives mass not only to the W and Z bosons, but to a whole family of fundamental particles, and it does so to different degrees in a way that shapes the entire structure of matter. To understand how, it helps to think carefully about what mass actually is. Mass is resistance to acceleration. That is its deepest definition. If you push on an object and it barely moves, we say it is massive. If you push on it and it leaps away, we say it is light. Mass is not weight. Weight is the force gravity exerts on a mass, and it varies depending on how strong the local gravity is. Mass is something more fundamental, the intrinsic reluctance of an object to change its state of motion. Push a proton and it responds. Push an electron with the same force and it responds much more readily because it is nearly 2,000 times lighter. The same force, very different accelerations. That difference is mass. Now, in the framework of quantum field theory, the mathematical language in which the standard model of particle physics is written, a particle is not a tiny ball. It is a vibration in a field. And the way a vibration behaves, how freely it propagates, how it responds to being pushed, depends on the environment the field is vibrating in. When a field vibrates in a true vacuum, in a background where every other field is at zero, it vibrates in a particular way, at a particular natural frequency. If that natural frequency is zero, the particle is massless, and it propagates at the speed of light without any resistance to acceleration at all. If the natural frequency is non-zero, the particle has mass, and it resists being accelerated. The Higgs field, by sitting at its non-zero value throughout all of space, changes the natural vibrating frequency of every field that interacts with it. It does this through a process physicists call coupling, the tendency of two fields to influence each other when they coexist in the same space. Think of two pendulums connected by a spring. When one swings, the spring pulls on the other, and the two pendulums begin to affect each other's motion. Their natural frequencies shift. They are coupled. The Higgs field couples to other fields in a similar way, and the strength of that coupling, how tightly the spring connects the two pendulums, so to speak, determines how much the natural frequency of the other field shifts, and therefore how much mass the corresponding particle acquires. This coupling strength is different for different particles, and it is one of the deep mysteries of the standard model that we do not yet know why. It is simply measured from experiment. Some particles couple very strongly to the Higgs field, others couple weakly, and some do not couple at all. The top quark couples most strongly of all the quarks and leptons, the family of matter particles. It is, as a consequence, the heaviest known elementary particle with a mass roughly as large as an atom of gold, though it is a point particle with no size whatsoever. The top quark's coupling to the Higgs field is so strong that it is almost as if the Higgs field and the top quark field are deeply intertwined. The top quark vibrates at a very high natural frequency in the Higgs field's presence, and that high frequency is what we measure as its enormous mass. The bottom quark, the next quark down in that family, couples significantly less strongly and is correspondingly lighter, roughly 4 times the mass of a proton rather than the top quark's 173. The electron couples quite weakly and is nearly 2,000 times lighter than a proton. The muon, a heavier sibling of the electron, identical in every property except mass, couples more strongly than the electron and is correspondingly about 200 times heavier. The tau particle, the heaviest of the electron family, couples more strongly still. And then there are the W and Z bosons, the carriers of the weak force. Their coupling to the Higgs field is also strong, and their masses around 80 to 90 times the mass of a proton. Reflect this. They acquire their mass through a slightly different aspect of the same mechanism, one tied specifically to the way the symmetry breaking works, rather than through the same coupling that gives quarks and leptons their mass. But the result is the same. The Higgs field is non-zero, the coupling is non-zero, and the particle is heavy. Now consider the particles that couple to the Higgs field not at all. The photon, the carrier of light and of electromagnetism. The photon does not interact with the Higgs field. Its field is structured in such a way, protected by symmetry, that the Higgs field settling does not break, that the Higgs background has no effect on it. The photon's natural frequency remains zero. It remains massless. And because it is massless, it always travels at the speed of light across any distance without resistance. The gluon, which carries the strong nuclear force that binds quarks together inside protons and neutrons, is similarly massless. It too does not couple to the Higgs field. It too travels at the speed of light. This is not an accident. The structure of the standard model is such that the symmetries protecting photons and gluons are precisely the ones left intact after the Higgs field settles. And the breaking of those symmetries, and only those symmetries, is what gives mass to the W and Z bosons while leaving the photon and gluon untouched. There is a common image that circulates in popular explanations of the Higgs field, the idea that it is like a crowd of people at a party, and particles are like celebrities moving through the crowd. A very famous celebrity gets mobbed, slowed down, made to move with difficulty through the throng. This image captures something true about the variation in coupling strength, but it is misleading in one important way. The Higgs field does not actually slow particles down. A massive particle moving at a given speed is not moving more slowly than a massless particle would at the same energy. It is carrying more energy, having more inertia, requiring more force to accelerate. Mass is not drag. It is something subtler. A more precise image is this. Think of a string on a guitar. When the string is slack, it vibrates at a low frequency, a low note. When you tighten the string, it vibrates at a higher frequency, a higher note. The Higgs field, by being non-zero, effectively tightens every field it couples to. It raises the natural vibration frequency of those fields. A higher natural frequency means the particle, the standing wave in that field, has greater mass. The Higgs field is not friction, it is tension. It does not resist motion. It changes the character of the vibration itself, permanently and everywhere. And that change, that shift in frequency, that raising of the natural note of each particle's field is the origin of mass for every quark in your body, every electron in every atom of every molecule of every cell of your hand resting on a pillow right now. The Higgs field, as we have described it, is not directly visible. You cannot point a camera at it. You cannot collect a sample of it in a jar. It is a background condition of space itself, as invisible and as universal as the passage of time. What you can do, in principle, if you have enough energy, is disturb it, create a ripple in it. And that ripple, the smallest possible excitation of the Higgs field, is the Higgs boson. The relationship between a field and its associated particle is one of the deepest ideas in modern physics, and it is worth taking a moment to feel it properly. Every fundamental field has a particle associated with it, the smallest possible wave or quantum that the field can carry. The electron field's particle is the electron. These are not separate things. The field and the particle are two aspects of the same entity, seen from different perspectives. The field is the background, present everywhere. The particle is a localized, traveling ripple in that background, summoned into existence when enough energy is concentrated in one place. Think of a perfectly still lake. The lake is the field. Now throw a stone into it, the ripples spreading outward from the splash. Those are particles. Each ripple is a discrete, countable disturbance. The Higgs boson is the ripple you get when you throw a very large stone into the Higgs field. The question is, how large a stone? How much energy do you need to create a ripple in the Higgs field? The answer is determined by the Higgs boson's mass, which is itself a property of the field's potential energy landscape, the shape of that Mexican hat. And for decades after the mechanism was proposed in 1964, nobody knew what that mass was. Theory constrained it to a range, but could not pin it down precisely. The Higgs boson could, in principle, have been anywhere from a few times the proton mass to several hundred times. The search for it became one of the longest and most ambitious hunts in the history of science. It required building machines of extraordinary scale and precision, machines whose purpose was essentially to recreate, for a fraction of a second in a tiny volume of space, the conditions that prevailed in the universe, a billionth of a second after the Big Bang. The machine that finally succeeded was the Large Hadron Collider at CERN, the European Organization for Nuclear Research, located near Geneva on the border between Switzerland and France. The collider is a ring, a circular tunnel buried roughly 100 meters underground, with a circumference of 27 kilometers. Inside it, two beams of protons travel in opposite directions, each accelerated to within a fraction of a percent of the speed of light. At certain points around the ring, the beams are steered into each other. The protons collide. When two protons collide at these energies of several thousand billion electron volts, where an electron volt is the energy an electron gains crossing a 1-volt battery, and several thousand billion of them is an almost incomprehensible concentration of energy in a space smaller than a proton. It is a collision between the quarks and gluons inside them. And in that collision, the energy is so concentrated that it can, very occasionally, produce a Higgs boson. The proton is essentially just a vehicle for delivering its quarks and gluons to the collision point. Two enormous detector systems, called ATLAS and CMS, each the product of thousands of scientists from universities and laboratories across the world, each representing decades of engineering and physics, surrounded the collision points and watched what emerged. They had to watch with extraordinary precision because the Higgs boson, once created, does not linger. Its lifetime is roughly 1/10,000 billion billionth of a second. Written as a decimal, that is a 1 preceded by 22 zeros after the decimal point. In that vanishingly brief existence, it decays into other particles, sometimes 2 photons, sometimes 2 Z-bosons, sometimes a bottom quark and an anti-bottom quark, sometimes other combinations. What the detectors see is not the Higgs boson itself, but the spray of longer-lived particles it leaves behind, like the afterglow of a firework that has already vanished. The challenge is that proton collisions at these energies produce enormous numbers of other particles too, backgrounds of ordinary processes that look, at first glance, rather similar to a Higgs boson signal. The two detector teams had to sift through billions of collisions, looking for the subtle excess of events at a particular energy that would indicate a new particle, and they had to be absolutely certain before saying anything. The standard they set themselves was 5 sigma, a statistical threshold, meaning there was only about a 1 in 3.5 million chance that the signal they were seeing was a random fluctuation rather than a real discovery. Science at its most careful. On the 4th of July 2012, in a packed auditorium at CERN, the results were announced. Both teams, independently had reached 5 sigma. Both had found the same thing, a new particle with a mass of approximately 125 times the mass of a proton, about 125 giga-electron volts in the units physicists prefer. It was consistent in every property that could be measured with the Higgs boson that Peter Higgs and his colleagues had predicted 48 years earlier. Peter Higgs, then 83 years old, was in the audience. He wept. The particle was real, the field was real, the mechanism was confirmed. And the question of why particles have the masses they do had, at last, a concrete, experimentally verified answer, rooted not in any arbitrary assumption, but in the specific value to which the Higgs field had settled in the first fraction of a second of the universe's existence, when it rolled down from an unstable peak and found its resting place in a trough that has not changed since. In 2013, the Nobel Prize in Physics was awarded jointly to François Englert and Peter Higgs, Robert Brute, Englert's collaborator, having died in 2011, for the theoretical discovery of the mechanism that contributes to our understanding of the origin of mass. Here is something that surprises almost everyone who hears it for the first time. The Higgs field, this remarkable, universal, ancient field that we have spent so long understanding, accounts for only a small fraction of the mass of the matter you are made of, a very small fraction, roughly 1% when it comes to the mass of a proton. To understand why, you need to look inside the proton itself. A proton is not a fundamental particle. It is a composite object, built from smaller things. At its core are 3 quarks, 2 of a type called up quarks and 1 of a type called down quarks, held together by the strong nuclear force, which is carried by particles called gluons. The Higgs field gives each of these quarks an intrinsic mass. The up quark has a mass of roughly 2 to 3 thousandths of a proton mass, and the down quark roughly 4 to 5 thousandths. If you add up the intrinsic masses of the 3 quarks inside a proton, 2 up quarks and 1 down quark, you get something in the neighborhood of 8 to 10 thousandths of a proton mass, about 1% of the proton's total mass. But a proton weighs 1 proton mass, not 1% of 1. The full thing. Where does the other 99% come from? It comes from energy, specifically from 2 sources of energy inside the proton, both connected to the strong force. The first source is the kinetic energy of the quarks themselves. Inside a proton, the quarks are not sitting still. They are moving very rapidly, confined within a space so small that quantum mechanics, the rules governing the behavior of particles at tiny scales, demands they move quickly. This is a consequence of a deep principle. The smaller the space a particle is confined to, the larger the spread of its momentum must be, and therefore the faster it tends to move on average. The quarks inside a proton are confined to a region about a femtometer across, a millionth of a billionth of a meter, and in that tiny space, they move at speeds approaching a significant fraction of the speed of light. They carry enormous kinetic energy as a result. The second source is the energy stored in the gluon field, the field of the strong force, that fills the interior of the proton and holds the quarks together. Gluons are constantly being exchanged between quarks, carrying the strong force. The space inside a proton is seething with gluon activity, and that activity carries energy. Now, here is where one of the deepest ideas in physics comes in. Energy and mass are equivalent, not just related, equivalent. The same thing, viewed from different perspectives. A system that contains a great deal of energy has a correspondingly greater mass. This equivalence, captured in the famous relationship between energy and mass that Einstein identified, means that all the kinetic energy of the quarks and all the energy of the gluon field inside a proton contribute directly to the proton's mass, not as a small correction, but as the dominant contribution. 99% of what you measure when you measure a proton's mass is, in this sense, the mass of confined energy. This has a remarkable implication. Almost all of the mass of your body, the mass of the protons and neutrons in every nucleus of every atom of every cell, is not mass that came from the Higgs field. It is mass that came from the energy of the strong force, from the ceaseless, rapid motion of quarks and gluons in the extraordinarily small and extraordinarily energetic interiors of nucleons. The Higgs field gave the quarks their intrinsic mass, the tiny seed around which the proton's energy organizes itself. Without that seed, the quarks would be massless, and the structure of the proton would be different in ways that would likely make stable matter impossible. But it is the beginning of the story of mass, not the whole of it. There is something quietly humbling about this. We spent decades searching for the Higgs boson, and its discovery was one of the greatest achievements of human science. The field it confirmed is genuinely fundamental, genuinely necessary, genuinely the reason the W and Z bosons are heavy and the weak force has the short range it does. And yet when you pick up your hand, when you feel its weight, its resistance to motion, the solid reality of it, almost none of that heaviness traces back to the Higgs field directly. It traces back to quarks and gluons moving fast in a tiny space, to the energy of confinement, to the deep equivalence of mass and energy that Einstein first articulated. The Higgs field is the key that unlocks mass, but the mass of your body is mostly the kinetic energy of particles you will never see, moving at speeds you can barely imagine, in spaces too small to have a name you would recognize. And all of that, the quarks, the gluons, the confinement, the energy, is made possible by the Higgs field having the value it does. Remove the Higgs field and the quarks lose their intrinsic mass, and the whole structure of the proton changes, and stable matter as we know it ceases to be possible. The Higgs field is not the whole answer, but without it, there is no answer at all. The discovery of the Higgs boson in 2012 was, in one sense, a confirmation, a closing of a chapter that had been open since 1964. But in another sense, it was an opening. And those questions point, quietly but insistently, toward physics that has not yet been discovered. The first and perhaps most pressing of these is called the hierarchy problem. It concerns the mass of the Higgs boson itself. The Higgs boson has a mass of approximately 125 times the mass of a proton. That sounds heavy by everyday standards. But in the context of fundamental physics, it is extraordinarily light. Here is why that matters. In quantum field theory, particles are not isolated objects. They are constantly interacting with every other field in the universe, emitting and reabsorbing virtual particles, flickering in and out of interaction with the quantum vacuum. These interactions affect the particle's mass. And for the Higgs boson, when you carefully calculate the contributions to its mass from all these quantum interactions, from its interactions with the top quark, with the W and Z bosons, with all the other fields it couples to, you get an answer that is vastly, absurdly larger than 125 proton masses. The natural scale for the Higgs boson's mass, if you calculate it naively from first principles, is something like 10 million billion times larger than what is actually measured. This is not a small discrepancy. It is the kind of discrepancy that tells physicists something is deeply wrong with the picture, or, more precisely, that something is missing. Some unknown mechanism must be at work, cancelling out these enormous quantum contributions with extraordinary precision, leaving a remainder of just 125 proton masses. The precision required is so extreme that physicists sometimes describe it as fine-tuning. The parameters of the theory would have to be adjusted to dozens of decimal places to produce the observed Higgs mass by coincidence. The universe rarely works by coincidence at this level. Several proposed solutions exist. A theoretical framework that pairs every known particle with a heavier partner. Particle, with a heavier partner particle would, if true, cause the enormous quantum contributions to cancel naturally, because the contributions from particles and their supersymmetric partners have opposite signs and would nearly cancel each other. The Large Hadron Collider has been searching for supersymmetric partner particles since it began operating. So far, none have been found. The partners could be heavier than the collider can currently reach, but their absence at accessible energies has narrowed the range of possibilities. Other proposed solutions involve extra dimensions of space, or the idea that the Higgs boson is itself composite, made of smaller as yet unknown constituents. None of these ideas has been confirmed. The hierarchy problem remains genuinely open. A second open question concerns the Higgs field self-interaction. The potential energy landscape of the Higgs field, that Mexican hat shape, has a specific, precise form, and the exact shape of the hat determines the precise way the Higgs field settled into its resting value, and the precise value it settled to. One way to probe that shape experimentally is to look for events in which two Higgs bosons are produced together, interacting with each other. This is called Higgs boson pair production, and it is predicted by the Standard Model. Measuring the rate at which it occurs would reveal the precise curvature of the potential energy landscape, effectively how steep the walls of the trough are, how the hat is shaped. This measurement has not yet been made. The process is extraordinarily rare. It happens far less often than single Higgs boson production, which is itself not common, and the current Large Hadron Collider does not produce enough collisions to measure it with statistical confidence. The high-luminosity upgrade of the LHC, planned for the late 2020s, is expected to collect enough data to finally probe this self-interaction. When it does, it will reveal something that has never been directly measured, the precise shape of the field's own potential. A third open question involves dark matter. Dark matter is a form of matter that does not emit or absorb light. It is invisible to telescopes, but which has mass and whose gravitational effects are clearly visible in the structure of galaxies and galaxy clusters. We know dark matter exists. But whatever it is, it has mass. And if it has mass, it may couple to the Higgs field, just as ordinary matter does. This makes the Higgs boson a potential tool for finding dark matter. If a dark matter particle couples to the Higgs field, then a Higgs boson could occasionally decay into a pair of dark matter particles. Dark matter particles, by definition, do not interact with detectors. They pass through everything without leaving a trace. But their presence can be inferred from the energy they carry away. Physicists at APLAS and CMS search for collisions in which a Higgs boson appears to decay into nothing, where the energy carried by the decay products is simply missing from the collision. So far, no statistically significant excess of such invisible decays has been found. The search continues. And then there is perhaps the most quietly extraordinary open question of all. It concerns the stability of the universe itself. The Higgs field settled into a particular value, a particular point in the trough of its potential energy landscape. But is that trough truly the lowest possible energy state? Or is it a local minimum, the lowest point in the immediate neighborhood, but not the deepest valley in the entire landscape? Calculations using the measured properties of the Higgs boson and the Tok quark suggest that the current resting value of the Higgs field may not be the absolute minimum of its potential energy. There may be a deeper trough at an enormously larger field value that the Higgs field has not yet found. If that is true, then the vacuum we live in is metastable, stable enough to have persisted for 13.8 billion years, but not permanently stable. A region of space could, in principle, spontaneously tunnel, shift by quantum processes to the deeper, truer minimum. That shift would propagate outward at the speed of light as a bubble of true vacuum, and inside that bubble, the Higgs field would have a different value. The masses of all particles would be different. The physics of matter would change. The bubble would expand without limit. This is not a cause for any concern. The calculations suggest that if the vacuum is indeed metastable, its lifetime is vastly longer than the current age of the universe, and the probability of such a transition happening anywhere near us in any reasonable time frame is negligibly small. But the fact that it is a genuine possibility, that the field we depend on for the very structure of matter may be resting in a temporary home rather than a permanent one, has a particular philosophical weight to it. The universe may be stable, or it may be very, very patiently waiting. The Higgs field has told us a great deal. It has not finished. Draw back now from the details, from the quarks and the gluons, from the colliders and the sigma thresholds, from the hierarchy problem and the metastable vacuum. Draw back from all of it and hold, for a moment, the widest possible view. The universe is not built on emptiness. That is the thing, the deepest thing, the thing that changes quietly the way you understand the word nothing. When we say a space is empty, we mean it contains no objects we can point to, no atoms, no light, no dust. But empty space is not nothing. It is a medium. It is a place where fields exist and have values, where the rules of physics operate with the same precision as anywhere else, where the Higgs field sits at its permanent, ancient, non-zero resting value, as it has sat since the universe was less than a billionth of a second old. The gap between the nucleus of a hydrogen atom and its single orbiting electron, a gap that, scaled up to human proportions, would be roughly the distance from a marble at the center of a football stadium to the stadium's outermost wall. That gap is not nothing. It is full of the Higgs field, threading through it at its full value, ensuring that if an electron were placed there, it would immediately have the mass we have always measured it to have. The space between the Earth and the Moon, 384,000 kilometers of what we casually call vacuum, is saturated with the Higgs field. The space between our galaxy and the next, those 2.5 million light-years of cold, dark, almost featureless void, also saturated. The Higgs field does not thin out with distance. It does not diminish in regions far from matter. It is as present in the deepest intergalactic dark as it is in the core of the densest star. It is, in this sense, the most evenly distributed thing in the universe. And it has been there at essentially the same value for almost all of cosmic time. The universe cooled and the field settled in the first fraction of a second. Galaxies formed and evolved over billions of years. Stars were born and died. Planets condensed from the remnants of ancient supernovae. Life emerged on at least one of them. Civilizations rose, and through all of it, the Higgs field sat quietly at its resting value, unchanged, conferring the same masses on the same particles, holding the structure of matter constant. There is something in that constancy that feels, if you let it, like a kind of steadiness. Not the steadiness of something rigid and unyielding, but the steadiness of something that has simply always been there, the way certain things that matter most tend to be. Think about what that steadiness makes possible. The electron has a specific mass because the Higgs field has a specific value. Because the electron has that specific mass, it occupies specific orbitals around atomic nuclei at specific distances. Because it occupies those orbitals at those distances, atoms have the specific sizes they do and the specific chemical properties they do. Because atoms have those properties, molecules can form. The long, intricate molecules of biochemistry, the double helix of DNA, the folded proteins that carry out every function in every living cell. Because those molecules can form, life is possible. The chain from the Higgs field's resting value to your existence is long and involves many steps. But it is a real chain. The Higgs field did not intend any of this. Fields do not intend things. It simply settled, in the first fraction of a second, into a value that happened to make matter possible, and it has not moved since. Your body rests heavily on a bed tonight. That heaviness, the weight of your arms, the pressure of your head against a pillow, the feeling of being held by something solid, traces back through the chain of physics to the energy of quarks moving fast in the cores of atoms, and to the intrinsic masses of those quarks, and those intrinsic masses trace back to the Higgs field. The Higgs field is the reason your body has the heft it does, the reason it can rest, the reason it presses down. The field is in the space between your thoughts right now, in the gaps between the atoms of the air you are breathing, in the nuclei of the calcium in your bones and the iron in your blood. It is not doing anything dramatic. It is simply there, as it has always been there, quiet and vast and patient. Physicist Matt Strassler once described the Higgs field as a cosmic stiffening agent, something that raises the natural vibration frequencies of the fields it touches, giving them the quality we call mass. That image has a certain rightness to it. Not a force that pushes or pulls, not a substance that slows or drags. Just a presence that changes the character of vibration itself, everywhere, permanently, without effort. The Higgs boson, that brief, fragile ripple in the field, lasting for a 10,000 billion billionth of a second before dissolving back into other particles, is the field's only visible face. The rest of the field is invisible, unmeasurable directly, known only through its effects, through the mass of the electron, through the heaviness of the W boson, through the heaviness of the W boson, through the weight of your hand. The stars are far away tonight. The galaxies beyond them are farther still, and in all the space between here and there, in all that cold, dark, silent distance, the Higgs field is present, exactly as present as it is in the space between your eyes and this darkness. Exactly as present as it was 13 billion years ago, when the first hydrogen atoms formed and the universe became, for the first time, transparent to light. Something settled long ago in the first moments of time. Something chose a direction, the way the pencil falls, and having chosen, stayed. And because it stayed, matter is possible. And because matter is possible, stars are possible. And because stars are possible, worlds are possible. And because worlds are possible, here you are. Tea heavy, warm, resting. The field is in the space between the stars. It is in the space between your thoughts. Let the thoughts go now, one by one, the way the day goes. The universe has been holding everything in place for 13 billion years. It will manage tonight. Sleep well.